Okay, and as you can see on the website embed2scale.eu, we see here the basic idea of embed to scale. So it's all about, as the name implies, about embeddings or vector representations of higher dimensional data. And you see here we have two data providers, so two data centers with different image or any geospatial data. We run through an encoder. This is basically of station model in our case at the moment. And the encoder compresses the data into a lower dimensional representation. And the only thing you need to transfer is the compressed encoder. And there are four categories of speedups we are achieving through this. It's embed to transfer, which you see on this diagram, where you save a lot of transfer time because you only send over the compressed embeddings over the network. Then there is embed to find. This is very, very interesting. So what we hear today from Duke is a little making use of this embed to find concept, where we compare similarities between embedding vectors to find similar images. And then we have embed to train, because if you only have the embedding and the decoder, you already have everything you need for fine-tuning your decoder. So you can think of this as a foundation model with a frozen encoder and an unfrozen decoder, because the pre-computed embeddings are nothing else than the outputs of a frozen encoder to the decoder, no? And the final one is embed to infer, where you can directly run inference on the embeddings because you have already a pre-trained decoder. It doesn't matter if this decoder has been obtained from training on top of a frozen encoder or on top of embeddings, but the decoder is all you need and the embeddings. So that's about the project. And then we have a very interesting and nice use case within the project. And it's basically a master thesis from Duk, who is in this call now. Now I will just transfer the microphone to Duk. Please fire away, Duk.
Thank you very much for the introduction, Romeo. Let me share my screen quickly. Can you see it?
Yes, we can see it.
Perfect. Okay. So yeah, my name is Duk, and in the last 6 months, I've been working on the topic of visual prompting, or to be more precise, visual prompting for geospatial image segmentation based on embeddings maps. And because the topics sound a little bit cryptic, I want you to imagine something. Let's meet Jan. Jan works for the government and he really loves the forest. He really wants to protect the forest, and to be able to achieve this goal, there are different tasks that he needs to do. So for example, he wants to prevent illegal loggings, he wants to track forest health or area, and also he wants to measure the forest coverage. And to do this task, he received some satellite images from the government, like this one here. And as you can see, it's very easy to see where the forest is, or where the non-forest is, or where the river is. And it's also easy to do it for one patch. But imagine you would need to do it for 1,000 patches. Now, in this case, there would be too many patches for Jan to do it manually. So Jan thought, maybe we can apply some machine learning to automate this process, maybe apply some segmentation models. So let's take a look at the right image where we want to segment the mountain area. So with the traditional approach, we would have some kind of pre-trained models. We would have some kind of labeled data, which are annotated by human. And then we would try to do some fine tuning on it, adjusting the model weight. This approach worked fine, but it takes a lot of time, and time that Jan doesn't have. So what is the alternative solution? So luckily, he found out visual prompting could be a solution for it. So instead of adjusting the model weight, we just provide the model some example, what we want to segment, and based on the example that we provide, the model can automatically generate the mask for us. So in this case here, we just provide some positive and negative prompts, what we want to segment, and based on this example that we provide, the model can automatically generate the mask for us. There are a lot of advantages with this approach. So it's very lightweight, and we don't need to do any fine-tuning at all. So how does it work behind the scene? So imagine we pick out one green prompt or one green click, which is brown, and we would compare this pixel that we pick out with every other pixel in the image to see how similar they are to each other. One intuitive solution could be comparing the color. That would work, but it would also introduce a lot of noise because, I mean, if you look at the image itself, there are a lot of different shades of green and also different shade of brown. So comparing similarity based on color only isn't the best approach. What we could do instead is to turn this pixel that we have into vector using, for example, TerraMine, a model that IBM developed, and then we can calculate vector similarity based on the vector representation for each pixel. So how can we turn each pixel into a vector? Let's do that with TerraMine for the image on the left side. So we have an input image. Because TerraMine can't process the whole image at once, TerraMine would divide the image into smaller patches, 16 by 16. And for this patch, TerraMine would generate a vector for it. Now, as you can see on the patch and also on the representation below, there might be a minor issue that could turn into a big issue because now every pixel in this patch has the same vector representation. So every brown one has the same vector representation as the green one, and that's not something that we want to have. You might ask, why do we even use 16 by 16 patch? Why not just 1 by 1? This has got predefined by TerraMine architecture, so that's not something that we can change quickly. So let's look at the results, how the mask would look like. So as you can see, the mask that got generated by TerraMine is very blocky, and it doesn't resemble the shape that we have in the input image. So the first research question that I asked myself is, what is the best way to map a single vector that we have to the 256 pixel in the patch? Does anyone have any question until now? Okay, I would say it is no. So let's take a closer look how we can map the vector to each pixel. So there are different approaches. I will go to each of them in details and then show you a benchmark at the end where I benchmark every method on 1000 patches. So let's start with nearest neighbor. So this is the easiest of all, where for every pixel we have, we just copy it. So for every pixel, we would get a block of pixel in the end. There's no averaging, there's no smoothing, it's just direct copying. So for every pixel that we have, we would get 2 by 2 identical pixel. In TerraMine case, we would have an upsampling from 1 by 1 to 16 by 16. And as you can see here, the result is very, very blocky. It's also reflected in the PCR representation of the vector. Now, the next method that I took a look is bilinear. So instead of copying each pixel 1 by 1, we would take a closer look at the neighboring pixel. So for example, top left, top right, bottom left, bottom right. And we would calculate an average of the surrounding pixel based on the distance. So for example, if it's closer to A, then A would get a higher weight, or if it's closer to B, then B would get a higher weight. And through this approach, we can smooth out the mask that we generate. So as you can see here, the mask that TerraMine generates is very smooth. But if you take a look at the PCA representation, you can see that it's very blurry what we generated. And to improve on that, there's another approach called guided bilateral. So while bilinear, we only consider the distance, guided bilateral also consider the color of the neighboring pixel. So what it does is calculate the same thing what we did in bilinear, but it also uses an RGB image as guidance. So it see how does the pixel actually look like in color, and so through that it can detect where the shape are, and when generating the mask, it wouldn't overcross it. So here is the final result. So as you can see, the masks are much more clear and they have a much better shape and edges. So the result is much better overall. And the final result, the final approach method is any-up. It differs a lot from the tree approach before because here we use a neural network, so it's not a static method. So we use a neural network that learn how to map vector to pixel. It's trainable and it's already been trained, so we can just use it right out of the box. If you take a look at the table, there are also a lot of other approaches that we can use. I just pick out any-up as a representation for this kind of upsampling method. And here in the end, you can see the four methods side by side, how they perform, and guided bilateral and any-ups perform the best. And to really quantify this result, I also run this on 1,000 patches. And as you can see, bilateral perform the best. If you look at the metric intersection over union, but I mean, if you look at all the matrices, bilateral works really like the best in all the matrices. Then to the next question. So after each pixel had its own vector representation, how do we calculate the similarity between them? There are also different methods how to do that. So for example, you can use cosine, dot product, or RBF Gaussian. So with cosine, you just ask, do the vector point in the same direction? With dot product, you also ask if they are aligned and strong. And with RBF Gaussian, you just ask how close are this vector in the embedding space. I also condensed this knowledge into a table, so it's more clear where the differences between the methods are. So with cosine, we just use the direction only. With dot product, we use the direction and also the magnitude. And with RBF Gaussian, we use the distance between two vectors. And here you can see the final results. I also ran the experiment on 1,000 patches, and cosine performed the best. But as you can see, all matrices, all methods yield the very comparable results, and it also makes sense that cosine performs the best because cosine take a look at the direction. So I mean, we ask ourselves, does this pixel belong to the forest and not how foresty or how green is this pixel? So yeah, so it makes sense that cosine performs the best. Now I would like to show you a demo how it would look like in the code. So here in the beginning, I import some dependencies. Then I here define the path where our patch lie. Then I load the encoder. I already ran this whole step before because it takes a little bit to run. And then we load the image. And here, at this step, we can provide the prompt. For example, I want to segment the mountain area. And here you can see those are the coordinates of the prompts that I provide. Now what I do is I would upsample them using guided bilateral, what I just explained before. And yeah, it's take a little bit to run, but it will be finished soon. And then after that, I can plot the PCA representation of the embedding space, how it look like. This one also take a little bit to run, but later on, what the next step would be is to do the cosine similarity. So we calculate how similar each vector are to each other. Let's see how long it takes to run. Okay, it's a little bit weird that it's taking longer than expected.
Maybe some questions from anybody in the meanwhile? Yeah, sorry.
Yep. And then we can generate the mass. And so as you can see, so based on the prompt that we provide, it can generate the mass for us. One thing that I want to show you that I will come to it later is uncertainty visualization. So if you take a look at the center plot, you can see where the model is uncertain that it belongs to mountain or not, and is always near the border. So the red area means it's very uncertain if it belongs to the mountain or not. Okay, let's come back to the presentation. So we just saw how TerraMine performs, but I mean, there are also other open source models on the market. So how does TerraMine perform in comparison to, for example, segment anything? So segment anything is a model that was created by Meta AI. It was trained on the segment anything dataset. The dataset contains 1 billion mass, 11 billion images. So one thing that I really want to highlight out is segment anything was trained on a very generic dataset, while TerraMine got trained on an Earth observation dataset. So it's much more fine-tuned for those tasks that we are doing here. And there are two models in this family. So SAM2 supports the positive and negative clicks that I just showed you before, but it also supports the text prompt. So you don't need to provide any clicks at all. You just need to provide a text, for example, fish or for a forest, and it can automatically segment the thing that you describe for you. If you look at the architecture of the model, it has a prompt encoder for the text and an image encoder for the image. Now I also ran the experiment on 1000 patches. And if you take a look at the plot on the top right, you can see that SAM3 text, where we just provide the text for us, perform the best. But one thing that I want to highlight out is that it doesn't produce any results for 1/3 of the patches I give to the model. So it doesn't provide any results for 334 patches. And if we consider those patches in the evaluation, then TerraMine would perform much better. I also pick out one sample so you can see how it looks like. So on the left side, we have the RGB image with the prompts, and on the right side, we have the ground truth. And if you take a look here on the mass from TerraMine, the mask that got generated cover most of the forest area. It also generates some masks for area which are not forest, but it's rather small. And if you take a look at the mask from Sam, you can see it doesn't cover the forest area at all, or it doesn't generate any mass at all. Now, let's come back to Jan. Jan thought, wow, TerraMine is so cool, and it's also very easy to do, but how many prompts should I provide? I mean, doing it with 2 or 3 prompts would be very quick, and I can do it on my own. But if I need to provide like 50 or 60 prompts, then that would take a lot of time. And to answer these questions, Jan created a data set of 10 patches, and he asked his friends, hey, can you please provide prompts for me? And they said, yeah, of course, I can do it. So the next research question is, how well does TerraMine perform when prompts are provided by the users? And to do this, actually, so while doing the experiment, his friend said, okay, I will try to provide a lot of prompts because then the model will perform better. Other friends from him said, I think I just provide the minimal number of prompts because it doesn't matter how many prompts you provide, the result would be the same. And to answer this question, or to answer this assumption, I create an application to collect actual clicks from actual user. Let me show you the application quickly. So the study already closed, but you can still go to the application to see how it works. So in the beginning, you will provide some information about yourself. For example, age, if you have any experience with the topic, or if you have any experience with annotating images, or if you have any color vision deficiency. After that, there's an instruction how to do the labeling. And then there's a practice round where you can practice a user. So for example, I will do some practice here. And yeah, and then the experiment starts. So you can just provide a positive and negative prompt as you want. And then you would do it for 20 images. Okay. So in the user study, there are actually 2 rounds. So in the first round, you can place the prompt as you like. So there's no concrete instruction how the user should behave. And for the second round, so there's a new instruction for the user where the user should actually place or make the prompt as diverse as possible. So what does diverse here mean? The prompt should have different color, should have different textures. There should also be some kind of distances between the prompts, so it's not clustered in the same area. And yeah, the assumption is with more diverse prompts, the model would perform better. So that's the reason why we have 2 rounds. So some information about the participants. We, in total, for the user study, I could convince 45 people to participate in it. Most people are between 18 and 34, and most people don't have any experience with the topic or never annotate images before. So I pick out one patch to visualize what the user actually provides. So as you can see, for example, on the top left, there are some users which doesn't provide a lot of prompts at all, just really the minimum amount is 1 positive and 1 negative. But there are also other users which provide like 80 or 90 prompts. So because of that, I took out this patch with a lot of prompts and gave it to the model to see how it performs. And here you can see the results of TerraMine at the top, and then also the results of SAM2. For SAM3, you can see that it doesn't work with many prompts at all. but it works if you just provide a few prompts. And below you can see SAM3 text only, so we don't provide the prompts, that just give out the text, and you can also see the segmentation mask as a reference. So if we actually take a closer look of how the study is structured and how many clicks each user provide, you can see that there aren't that much different between round 1 and round 2. And properly, so it's one assumption for me, is that people automatically diversify their clicks already in the first round intuitively. So as you can see, there aren't that many different between round 1 and round 2, so you don't even need to tell the user to diversify the clicks because they will automatically do it. And this is the final result. So for both SAM2 and Terramine, you can see that the result doesn't really differentiate that much between the two rounds. And you can see it even decreased a little bit. So based on the experiment, we can say more prompts doesn't mean better results. So that leads to the next research questions. How many prompts should I provide, and where should I put the next prompt for better results? And to answer this research question, it consists of two parts: prompt aggregation, which answer the questions, how do we combine information from multiple prompts, and prompt placement, where should the next prompt be placed to improve the results. So let's take a closer look at prompt aggregation first. Imagine we have this patch here with 3 positive prompts, which are provided by the user. And based on this 3 pixels, we can generate 3 positive vector. Now we pick out one random vector here on the top left, and we ask ourselves, okay, does this belong to the positive? Should this vector belong to the mask? How do we do it? And the first method, what we could do is aggregation. So what we do is we aggregate all these positive vectors that we have into one super point, and then we would calculate the similarity to the super point. And based on the results, it would be either belong to the positive mask, to the foreground mask or background. And we would also do the same thing for the negative part. So we have one positive super point and one negative super point, and we calculate similarity to both of them, and then we calculate the differences between both. That is the first approach with super point. The second approach is to calculate the similarity to each single vector that we have. And after we do that, we would calculate the average. So if it's closer to 1, it means it belongs to the foreground. If it's closer to 0, it means it belongs to the background. There's also another method that we could do, which is max aggregation. So here we only we don't need to do much calculation at all. We just said if the random vector that we pick out had a very high similarity to one of the positive prompts that the user provides, then it should belong to the mask. And that's it. So as you can see, there are 3 methods that we can do, or 3 class, super point, and every single point. And now let's come to the second part, from placement. So imagine we have this patch here, and there are already some prompts provided by the user or automatically generated. And you can see the mask and also the area which are missegmented. So where should we put the next prompt so we can improve the performance? One way, what we could do is to first identify the region which are missegmented. So in total here, we have 5 regions which are misclassified. And then we pick out the biggest region and put one prompt in the center of it. So it's just a very naive way to do it. And we would just do it 10 times, so 10 rounds. We would just put the next prompt, calculate where the next biggest missegmented region is, and then put the next prompt there. And we would do it for 10 rounds. So as you can see here, for this patch, the performance is already very high, already from the beginning. But if you look at other patches in the data set, you can see that it gradually increased based on the prompt that you provide. So that's one way how to do it, where we only click on, where we will provide the center click in the missegmented region. The next thing we could do is to calculate the uncertainty. So where is the model uncertain that it belongs to forest, and put the next point there. So you can see it here. So it's the uncertainty is always high where the border is. So because this example might not be very clear, I took out the one example that I showed in the demo. You can see that the model is always very unclear near the boundary. So what the model would do is, what we would do is put the next prompt at the boundary somewhere where the uncertainty is high, and then calculate everything again, do it for 10 rounds. So in total, we have 4 components: super point, every single point, center click, and uncertainty-based sampling. And if we combine them together, we would have 4 combinations where we test out each combination strategy. There's also a baseline where we just put random point where we see the mass, and we just put one point randomly somewhere. So it just should act as a baseline to see if this strategy that we created actually improve anything. And here is the final results. So all 4 methods had a higher performance than the baseline, and max aggregation with uncertainty sampling yields the highest results with over around 10.5%. And if we click a closer look how the improvement looks like, you can see that the improvement increased significantly in the first round, and then it decreased for every prompt that you set. And after round 6, you almost got diminishing returns. So the performance of the IOU doesn't increase anymore. So to answer the question, how many prompts Jan should set, I would say it shouldn't be more than 10, because a few, if they are placed in the right area, this should already be sufficient. And yeah, so thank you very much for your attention. And Jan is happy because now he knows how to do forest segmentation with Terramine, or do segmentation with Terramine overall, and he can finally protect the forest. Do you have any questions?
Olivier, can participants unmute themselves? I mean, you didn't see it, Doug. I answered quite some questions in the QA section.
Can you hear me?
Yes. Yeah.
Okay. Good.
Well, thanks for your presentation. That was cool. I do have a question. First of all, you tried to distinguish with the 2 different classes, like water or forest or mountain or forest. They are distinguishable. But what if we do have more than 2 classes? For example, in each patch, we have 5, 6 classes, and we cannot distinguish them easily, like a grassland and forest and cropland. You know, they are more or less, they can be the same. So did you try to see how prompting works in this situation?
Yes, that's a very good question. And that is also a problem that I encounter during experimentations, because, for example, on the data set that I have, there are different type of forests, for example, mixed forests or broadleaf forests, and the model can't really differentiate as a specific type of forest, or really differentiate is it grass or forest or something like that. It can just be generalized. So it can just say it's forest, but it can't say what specific type of forest it is. So it's probably the same thing with grassland or river. If there are different type of subtype of river, then it can just say it's a river, but it can't say which type of river it is.
Well, good. And the last question is about, did you try to first, for example, I'm just guessing that the fine-tune the TerraMind with the masks, and then you use the prompting to see that how the, let's say, the results can make better.
Yeah, I didn't try it out. So, but that is one of the things that can be done in the future.
Yeah. Good. Thank you so much.
Yeah. Thank you for the questions. Are there other questions? Yeah, I think that should be it then.
Maybe what I can do is I answered a couple of questions in the QA section. Maybe let me just briefly. And by the way, you can just got the message from you can raise your hand. If you have questions, then Olivier can unmute you. And while you are thinking about raising your hand and your question, I just want to say something about the already answered questions. So someone asked if he will have access to the code. So this code will be available in the TerraPort GitHub repository soon in the examples folder. Then there was another question of what data we used. So we used Sentinel-2 data, and the current version of TerraMind is optimized for low resolution, so for Sentinel-2 resolution, but folks are working on the next versions of TerraMind. And then, yes, this is all will be available in TerraPort. And then one question was how the number of points is influencing the performance. This is something to answer now. And then the question about multi-class classification. This is future work. No? Then let's see. And TerraMind can handle multiple resolutions and modalities. I mean, that's one of the key features of TerraMind, that it handles multiple modalities at the same time. And then there was a question how it differentiates to Alpha Earth. So we have in the Kieu Bench 2 benchmark, we compare TerraMind to many other models. So you can have a look there. I'm not sure if Alpha Earth is there. I don't think so. That is something you would need to run for experiments. And then someone recommended that we should have used Dino V3. And yeah, this is something we can also consider in future work. And I just got a message from Benedikt Blumenstiel, who is also in the call. Oh, he's saying TerraMind cannot handle multiple resolutions. It's something which, but it can handle multiple modalities. Okay. Did someone raise their hand? Is something, Olivier, can somebody unmute them? Or are we good? Not seeing this here. my side, it doesn't look like. Huh? Okay, Tuk, I think we are done. No, you can say goodbye and thanks.
Yeah. So thank you very much, everyone, and thank you for the time. And yeah, see you next time. Well,
by the way, next month we have another, let's say, sandwich hybrid call in the Earth to Back call. Then Lindy will present her master thesis about embedding space matrix constraint fine-tuning. So the idea is we found out that we can apply a certain metrics on the embedding space. And oh, my name changed to Romeo Kinsler in the meanwhile. Thanks, Olivier. And it's on 24th of April. Yeah, and then using those embedding space matrix, she constrained the loss function, and therefore the embedding space is shaped to favor certain embedding space matrix, and she did a comprehensive performance analysis. So stay tuned, and thanks a lot for joining.